A little bit about me. Staff software developer at Black Diamond Wealth Platform. We have a recruiting site at www.ascii-value-blackdiamond.com. Use the ASCII value. The other one doesn't work. Just use the other one. Anyways, the GitHub for all of the demo code that I'll be showing somewhat at the end will be at that GitHub address. If anyone wants it, I can give it to them directly. So the focus of this talk is going to be really only three things: challenges of distributed computing, data sharing and code reuse, and gRPC and how it helps to solve some of those issues that you run into when building distributed systems. Also, disclaimers. This entire talk is based off of personal research and observation, and is certainly not a compendium on solutions for distributed computing problems, because there are thousands of ways to solve problems. This is just one of many. So, just because there's tomorrow Azure comes out with some magical event source-based system, it's not my fault. So, what are some of the concerns when building distributed systems? First and foremost are probably how you partition your domains in your future distributed system, and how you compose those now partitioned domains as a process. You're building an order system, you're going to have customers and orders and carts and whatnot. Each of those is a domain. How do you compose them together? That tends to be a core problem. You get the partitions wrong and it makes everything harder down the line. The other one is communication. Obviously, between those now partitioned services, you're going to have to communicate between them to get data, manage contracts, whatever, and that is overhead and problems. The other is sharing and reuse of data or behavior. I'm kind of reading from the slides, but there's not really any other way to paraphrase this. So regardless of what world you go into, you're probably not going to be able to build a system that's completely isolated from everything else. So you're going to have to share data between these systems. A lot of times you hear the term CAP theorem. It's not all that complicated. Consistency, availability, partitioning. Problem is, you're building a distributed system. You don't get to choose to not do partitioning. You're a distributed system. It's partitioned. So you get C or A. So availability or consistency. If you want more information on that, there's 1,000 blog posts. Go for it, or I can talk to you afterwards as well. Still not done with that slide. The other thing you worry about is how fast is it to build services when you're in a distributed system, or build features even. So if you deal with a normal monolith, large application, building features potentially breaks many other things. You have to deal with maintenance of that. It tends to be really fast to build small systems that are isolated, and slower to build on really large systems. But it's something to think about when you're deciding whether to partition a certain domain or to put it in an existing domain. API versioning and backwards compatibility. You have hundreds of services that communicate with each other. They're not going to not change. They're always going to change. These services are changing left and right. You have teams working on service A, teams working on service B. They're going to communicate. You need a contract. It's going to change, so it's something you have to think about. And of course, testing. I'm not even going to talk about this. It's present there. You could do a whole presentation on that, but it's complicated doing testing across a distributed system because you have to deal with many integration points. So I'm going to rush through some of these slides because they're just general talks on building distributed systems, particularly domain-driven design, how you create your aggregate routes, bounded. I'm sure a lot of people who've went into domain-driven design have heard the terms bounded context, aggregate routes, all that kind of stuff. Basically all the buzzwords you hear when you talk about domain-driven design, but the concept is domain partitioning is how do you decide what goes in a particular service when you're building it, and what and how you communicate to other services from that service. And again, you communicate to other services through interfaces, whether it's API, events, gRPC, or whatever. So, and you'll see a general theme as I go through this, is that gRPC is not the only solution for most of these problems. gRPC is just a solution that tends to work really well for specific use cases, or if you're looking for certain features that gRPC provides, which I like. So going into performance concerns, the guaranteed to have networking serialization between services. You're going to have to go over HTTP or some other medium. You're going to use JSON. You're going to serialize left to right. Overhead that you have to deal with. How are you going to scale it? How are you going to manage memory? If you're doing a file server and you are serving up 100 gig files, terabyte files, really large files, you're not going to be able to pull that into memory, right? You're going to have to decide to stream that over the wire. Well, if now your file server is really far away from your client and you don't want them directly connected, how are you going to get this 1 terabyte file all the way over to this other system? You can't pull that 1 terabyte file to every single hop along the way. Also, another really big thing with distributed systems is data locality. So you have one system that saves data into Mongo, you have one system to save data into SQL, one system saves over to MemSQL, and tomorrow you need something that aggregates all that data together. Well, if you don't have certain things in place to have that data in the same place, which is data locality, then you are going to run into performance issues. You're going to have to build, however many ETL processes that you want to deal with, and just not particularly great. And also, if you are focused on the C of CAP theorem for consistency, you're going to have to deal with distributed transactions, which is its own performance overhead as well. So keep going. If anyone has any questions as I go through with this, of course, I am talking relatively fast because the demo there's a lot of stuff in the demo. So I want to kind of get to that.
Challenge here, whenever you make 2 different API calls, but they need to occur in a kind of a consistent distributed transaction. Like I have 2 different services, one for calling payment, other one calling for updating my database. But I cannot make it as a single transaction oriented with automaticity wise, like if one fails, the other should roll back. In those scenarios, how do you control that in the distributed mode?
So I kind of will go into that, but there's a couple different solutions. Some that are not great and some that are complicated, none that are simple. None that I know of that are simple, let's phrase it that way. But the answer normally is you need to write, is something like event sourcing, where you would write to an event store and then you emit events out to both of those systems and make sure that they're consistent. However, if they're not, if you have an issue with the writes to any of those systems, you have to emit compensating events and all this kind of stuff, which makes it really complicated. So
in this case, the credit card transaction already processed. I got the acknowledgement back. When I'm trying to update my database, it failed. Now I cannot reverse the transaction back again.
Right.
Unless I post on a reverse cancellation transaction kind of stuff. This is what we are real-time challenge we are facing now.
Yep, and in that kind of behavior, by allowing the commit to the transaction system while allowing the other system to not be more or less consistent with that transaction system, you are kind of relying on the availability. You're leaning towards the availability of CAP theorem, right? You're not going with the consistency. So if you really want true consistency, then you really have to use something that facilitates distributed transactions. Whether you use something like end service bus, which again is just one form of distributed transactions, or various different 2-factor commits or outbox patterns. There's a couple different patterns to put into place, but it's not easy.
Both the services are provided by 2 different vendors, so I cannot have control on mandating another one.
Yep, and you normally have to have either compensating events or some sort of process that pulls and forces the systems into consistent state as a post-processing event.
I mean, we are lucky enough, at least only 0.1% of the transactions are failing, but if it's more, then definitely we'll be in big trouble actually.
Yeah, we can probably talk a little bit more afterwards if you're curious and see if we can find something.
I'm not in the specifics, that's why I'm thinking down to the distributed model. That's a major challenge actually.
Yep. Yeah, so that's perfect example that fits to the sharing concerns and the previous one, but I'll keep going. Other things that you have to worry about is you have lots of contracts, you have lots of teams, you have lots of people doing lots of things. How do you get your contracts to other teams? How do people know when you've updated contracts? How do you pull in those new contracts? Who manages those contracts? Do you even care? All things to think about when you're building a distributed system with a distributed team. For reference, if you're just one team building a distributed system, then you don't have as many concerns, but that's different conversation anyways. Data sharing, kind of already discussed that. Backwards compatibility and versioning also leans towards the API versioning as well. As you're versioning your APIs, you need to be able to have backwards compatibility for services that can't stay up to date with your latest contracts and manage versioning of your API. All right, going on. Another concern, major concerns in distributed systems is how fast, the time to deliver. Like how fast can you get out to production? Services that operate in isolation are really fast to make. I can throw together a service that manages customers in a couple hours, but that's completely useless if no one's using the data. So you have to think about kind of the trade-offs of, hey, I'm making this service in isolation, but who needs the data from this service? Where is it going? How are you sharing that data? And also, now that you have 20, 30, 40 different services, how do you manage the continuous integration and continuous deployment process? Every single service has to have their own deployment process, or maybe different Jenkins files, or if you set it up all in Docker, you still need Docker images and a registry and all that kind of stuff. So these are just general kind of things to think about, and I will go over some ways to solve these in the demo as I go on. So as most of those slides had something related to data on them, and it's perfectly related to the topic that he was talking about earlier, is one of the hardest problems to solve in a distributed system is data, period. Data is always the hard problem, is you need to share data. There's no way you're getting around sharing data between systems. Foundational data, whether it's security, configuration, transactions, those have to be shared. And you have to, and there's many ways to manage them, or many ways to do that, and it really all depends on your needs. So, and as it says, most are complex, hard to maintain, don't scale well. One easy way, as many people from Black Diamond might notice, is you just have one database. Shove it all in one database. We're good. You don't need more databases. It's fine. And then you don't have to worry about distributed transactions. You just one transaction. It's fine. Other option is you share packages, NuGet or NPM packages that go and get your data. Well, then you have 1,000 different apps reading from the same data source. That's not maybe the greatest way, but still a way to share and might be valid for your use case. But yeah. And the other ones are APIs, request response, whether you use web API, 1,000 different ways to do APIs. Everyone knows what an API is. There's no real, I don't need to get into that. And of course, eventing, which tends to be one of pretty much a requirement in any distributed system, is some sort of eventing process. Whether it's true event sourcing, or if it's post-processing events, or however you plan to do it, chances are if you have a distributed system, you're going to have events. Don't be afraid of events. You're going to need them. And success regardless with any distributed system, in order to have a successful distributed system, you're going to have API-based communication abstractions. So AMQP, which is any message bus or any messaging system, HTTP, or gRPC, as I have for this talk. Shouldn't be too many more of these till we get to demo, but we'll keep going on. So one of the things that we talk about in team at Black Diamond occasionally is the term distributed monolith. And we're going all the way back to the term having a single data store is you can have 1,000 services, and if they're all reading from the same data source, you're not really a distributed system. You're a semi-distributed system, and that's why we like the term distributed monolith, because you're really still in a monolith scenario. It's easy to use the data, but it's hard to decouple the data. Teams always step on each other's toes. You're running into schema problems. No one wants to change schemas because it breaks 10 apps. Nightmare. Relative nightmare. Might be good for small scales, not as good for larger scales. So I'm going to go through this real quick. Of course, one of the solutions is event sourcing, and people who've heard the term CQRS are very familiar with this. Of course, it solves many problems. So use it if it makes sense. However, there is a significant amount of operational overhead for event sourcing, and you have to build it into your system, and it has to be kind of first class in what you're doing. If not, you're more or less emitting events after something happens and not as something happens. And of course, I kind of just talked about some of these, but a couple of the problems with eventing are if you're not doing true event sourcing, then you can miss events, you get duplicated events. And even if you are doing event sourcing, what kind of events are you emitting? Are you emitting single change records, like I changed a customer record? Or are you emitting, or particularly a cart is a great example. Are you emitting an event that says, here is a cart item has been added, or a cart item removed? Or are you emitting, here is the cart, project this into your next system as you want it? Decide which one you want. It really depends on the system that you want or you're dealing with. Consistency issues is, of course, the same problem as we were talking about before. You're always going to run into consistency issues unless you do some sort of distributed transaction work. And again, it all kind of needs to be built from the beginning. But it doesn't have to be. It's a whole lot easier if you just build eventing in from the beginning, and you don't have to worry, even if you're not using it. It's just helpful to have those as a future need. All right, now we're actually getting into the gRPC piece of things. That's kind of just the overview of why distributed computing is hard. Not that anyone here thinks that distributed computing is easy. If it was, then you probably wouldn't worry about all these little things. But gRPC is a tool to solve some of those distributed computing problems. It uses HTTP2 as a transport medium. It allows for two-way communication. Clients can send multiple messages. Server can receive multiple messages. You can go back and forth and deal with it as you need. We even floated a concept of doing a distributed transaction with gRPC, in that you can start a SQL Server save and start a Mongo save, and then the SQL Server save fails and you revert the Mongo transaction, and we're like, well, we should just really use a distributed transaction if we want to do that. But theoretically possible, not necessarily the greatest idea. But the serialization process for gRPC it uses protobufs. It's a binary-based serialization, so it's relatively fast. You can compress it. You can do all sorts of things that you want to it. It's one of the fastest means of passing data from a system to system. And the contracts for protobuf files are relatively easy to read, and I will show you those in a moment. The provided tools, Proto-C, which Google provides, they have all sorts of different, it's a GitHub project, you can pull it down and check it. But all of the proto files can be used to generate various different clients or servers for, I don't know how many languages there are, but there are very least 5. I have 5 on the slide. But the demo will have both Node and C# generated stubs. So some of the things to think about, obviously, why would you use gRPC? What's the point? gRPC is still HTTP, you're still sending messages, you're still receiving responses. So what really is kind of the benefit of gRPC? One is there's really less ceremony in setting up a gRPC communication, right? So you have a proto file and the server, and you distribute the proto file, which I'll show you soon. and you kind of just generate your client and you use it. Now, it's not that HTTP APIs aren't relatively easy to work with either, but gRPC tends to be faster and cleaner, and you don't have to worry about slight idiosyncrasies of server responses and certain type of error sources and various underlying pieces. So it's just a slight bit less ceremony. I'm not going to go over each line item. This is way too much to go through. So just the slides will be presented out if you're really interested in the different ceremonies, but different languages also have slightly different ceremony in itself. So now we talked about what gRPC is, and now we talk about what gRPC isn't. In my opinion, and in most people I talk to, gRPC is not a replacement for REST. I would not suggest exposing a gRPC client to external or gRPC endpoint to external clients. It's just not as easy to certain REST APIs lend really well to sharing with external systems. gRPC lends really well for sharing in internal systems. So inside of a single company or inside of a team, you gain a lot more from using gRPC there than if you tried to expose it as an external medium or external endpoint. So also, when using REST, you can end up with a whole lot of routes depending on how you build out your system, and you might not really, service one might not care about these 10 routes, but you still have to go in the documentation, read through all the 1,000 different lines of routes and figure out what they all do and whatnot. At least with gRPC, it's relatively easy. You generate your clients, and normally, depending on your IDE or depending on the tooling that you have, you can get relatively easy IntelliSense, documentation's right in there. You can have it all kind of nice and built in your proto file that you can read. It tends to be nice. Also, as I think people have seen in other talks, gRPC is not SOAP. And it's not SOAP because WSDL is horrendous. I don't know how many people have dealt with WSDLs. I hate WSDLs. It's not readable at all. XML is verbose and not performant. And of course, HTTP is essentially limited in a sense in that you're not getting two-way communication, and you're limited to HTTP and not HTTP2 kind of style messaging. And also, of course, gRPC is not a replacement for messaging. So gRPC is still a synchronous request. You're making a request, server's getting that request, making a response. Whether you send it a bunch of times, doesn't matter. The concept is it's still relatively synchronous. Messaging and events are not synchronous, and they shouldn't be. And there's a lot of benefits to having an asynchronous process in a place. And also, gRPC does not have more or less built-in competing consumer processes. So if you have 13 gRPC services running, and you're hitting one, you're not really getting anything, right? You still need a load balancer in front of gRPC. It's still HTTP, it's still web traffic. You need a load balancer in front of it, whether you use a built-in Kubernetes ingress, Nginx, F5, doesn't matter. You still need a load balancer in front of it. It does not do competing consumer for you. All right, so at this point, that's when kind of I'm going into the demos, and I kind of have this slide set up where I'm posing a problem that we kind of ran into as we were building the demo, and the solution, some of the solutions we were thinking about as we were building it. First one is we built a file server because, why not? We just built a file server. And we built it on top of Mongo, and people are saving files into Mongo. But we decided that we actually, instead of wanting to serve files, we really wanted to stream videos because everyone loves videos, and that's just how it is. And we were like, we really like Twitch. Maybe we should make something Twitch-like. So there's a couple different ways you could do it. You could obviously make a shared package to access those Mongo documents or Mongo blobs directly, read them right out of Mongo. Again, not great, kind of works. You can build REST service APIs on top of it. Or, of course, what we actually did is do a gRPC stream. So, and yeah, I added this slide. So this piece right here, this is kind of a diagram of the end demo. Don't have to read it. The main piece that that I'm going to focus on is this is what's in place. It's file server in Mongo, and this is what we wanted to build is a video server on top of it. So as an example of what you might do, you might just want to go ahead and build a quick gRPC service, and of course it has to run in admin mode for some reason, who knows. So I'm going to just do a quick demo of how easy it is to build. And for reference, I'm also using all of it's ASP.NET Core 3.0 Preview 6. Preview 7 just came out 2 days ago. I was not confident enough to pull that down for the demo, so this is using a lot of the new functionality built into ASP.NET Core 3.0 for gRPC clients because they built in a lot of first-class framework support for it, and it's really nice. You'll see. Yes, 3. Also something that comes with ASP.NET Core 3 is a template for a gRPC service. Convenient, of course. It comes with the SDK, so you get a scaffold out gRPC service. And you see it scaffolds you out a little greet, hello world, more or less. Come on. And this is, so you can see a quick basic proto file. I'm not going to go into this one because I'm going to go into another one relatively later, but more or less, these are methods. These are objects, and the methods take the objects and return the objects. You get that. So, say I did have a file server, which I, of course, do. And I have a proto file in this file server that represents the server that's doing it. It has a couple methods: get file info, remove file, list file, download, upload, blah, blah, blah.
Can you zoom in?
I can. If I remember what the hotkey is. Control plus. Bam. Is there presentation mode?
Yeah, well, now that you've seen it go.
Yeah, that probably would be a problem. So you have the proto file here, and something you might do is you're like, okay, I have the file server, I have the code. I'm going to just go ahead and copy that proto file for now and see what happens when I drop this thing in here. And of course, no one loves the copy pasta. Excuse me. It didn't copy. Complain. Anyways. So I'm going to drop the protos file in there. I'm going to go ahead and... What are you complaining about? What are you guys laughing? All right. The thing that I'm going to pull, this is a package, and of course they decided to upgrade the version, and so we'll see how the world works. It was a pre-1 before. Client Factory is a nice little tool that comes with the, yep, didn't work, so I'm going to go pre-1. It is for building gRPC clients. If anyone's used the .NET Core 2.2 HTTP factories, it's very similar in that it's really easy to wire up. And I'm going to pretend that I magically built this service and steal some code. And the only thing you need to do in here is edit this directly because it makes it easier. So if you notice in the CS projects that they have protobuf entries now in here, and this was a scaffold out gRPC server. However, I also want to make a client, and I want it to be pointed, I want it to use the files proto as a base, save that guy, and I'm going to discard, yes. And now, even though you don't see it, it has, on build, it will generate the actual client. And then I can just wire it up right here. That is not what I copied. Live demos is how it works. And you will see it will auto resolve this now, because the gRPC file server definition was set up to have an underscore gRPC file server in it, because it was actually implemented in Node. And this gRPC add gRPC client is in the package that should have been downloaded, but you get the idea. And I'm going to go over to the actual implementation. But the point is, if you add the proto to the CS proj, set it in client mode, it will auto generate all of that on build, and you can start using it. And you can actually look at the generated code if you want, though it's not that beautiful, which is why it's a whole lot easier to just look at the proto directly so you can manage the methods. So that all seems nice, except I hate the idea of copying a proto file from another source to this one, because hey, if I update the proto definition, what are we going to do? Then you have to copy it to every single file or every single service that you then use that file in. It's not really a scalable process. So say we created a gRPC service, but now the teams need to distribute proto files and the contracts underneath them. And ignore those. What's a proto file? A proto file is a definition for an implementation of a gRPC service. That's really all there is to it. Proto file is the extension for protobufs, but it's a definition for gRPC connections. It's more or less the contract. It is the contract. So, say we need to distribute that process. We need to distribute those proto files. So we need to build a CI/CD pipeline around the proto files. Building clients for proto files is relatively easy. Normally you'd run proto C. It builds the proto files. You put it in whatever format you want, and then you distribute it. However, ideally you'd want to be able to put the proto files in a NuGet package for C#, an NPM package for Node, pull those packages in and reference them directly. So, as an example of how you would do that, I did it. And you can see there's Jenkins. I have a local Jenkins running that is set up to look at this repo, and each one of my individual servers which have a proto definition in them, I have a build folder that represents the builds for individual proto implementations. So this would be a Jenkins file for a NPM package build, which you have your package JSON with the reference to the proto. And very similar to NuGet, you have a process to build that NuGet package, which is more or less that compiled code that you saw earlier that was auto-generated on build. But now you can do it via Jenkins and publish it via NuGet. So CS projects are relatively easy. You just reference all protos. And if you're curious of the specifics of these Jenkins files, I can go into it later. I am using the Docker plugins for Jenkins to kind of pull down the specific SDKs I care about, but there's some caveats specifically with .NET Core that make it a little bit irritating, but it's not too bad. So each of these protos has, or each of these servers now has the representation of builds out to NuGet and NPM. Say you had Go services that needed proto files or whatever the Go package manager is, I forget, Python, whatever you want, you can just make a definition for each of those, and then you're really just publishing it as if it were a normal package. So I need, I did not set the admin password. If there are any questions during this whole process, just ask me. So in this Jenkins, it's set up to point to all of my individual proto files, each individual NPM NuGet representations, and as you would guess, I do a tag-based, or not guess, but either way, I do a tag-based system, and in each of these processes, you can see that for each of these tags, it just builds it and moves on. And it right now I have it set up to publish to a local NuGet and a local NPM. So you will see it in NPM and NuGet. Get through this. So I have these proto files published over here, and if you download these packages, what you'll see is you'll see the proto files in there. And for the NuGet one, I have it set up to actually compile artifacts as an example. So it compiles out a DLL and you can include it in your project, and you don't have to have any entries for the proto file in your project. For the Node one, it's more interesting because you have a little bit more flexibility with Node. And Node has a way of runtime reading in the proto files and generating the contracts. So you don't even really have to have any build time artifacts at all. But you can also optionally build out your JavaScript files that are the resulting clients. So I'm not going to show you the details, but these are just NPM and NuGet packages. And you can easily just reference them the same way you reference any other NuGet package. And in, nope, it's the video server. And right here. So you just reference them like a normal package, and now you're all good. So one of the problems that I mentioned with distributed computing is sharing contracts. How do you distribute your contracts across teams? Easiest way, Proto makes it really easy. You just define out your builds for each individual language that you really want to distribute, and you pull them down as if they were any other normal NuGet package. Could you do that with APIs? Yes, but it would be a whole lot more to manage individual JSON contracts and all that. You have kind of everything built into the proto file, and just makes it really seamless and easy to integrate with existing services or new services. So, any questions about that particular piece, or if anyone wants to dive into any of those more?
Based on your recommendations, they seem like, would you see like a company sort of needs a lot of infrastructure in order to implement this SOA distributed system approach with all the NuGets and local NPMs and everything? It would be like a lot of infrastructure.
So it depends, right? You could obviously you don't necessarily have to distribute the contracts via a NuGet or NPM registry. If you have 6 or 7 teams that are working, it just really is easier than saying copying out a proto file across the things. Obviously, when you're dealing with REST APIs, you have a service definition that you can adhere to, but then you're dealing with versioning around those REST APIs is where things get really complicated. Is when you upgrade versions of REST APIs, when you change them and contracts change, then you don't really have an easy way of identifying those contract changes outside of some sort of service discovery implementation around your versioning, or if you slash v2 on there, but you're still going to have people hitting your previous version. The nice thing about protos is there is a built-in way to deal with versioning. So protobuf files, as you saw, and here really have indexes for the field items, because when this is actually serialized, you don't have any of these names in place. So when this is serialized, it's just going to be 1s, 2s, and 3s and whatnot. So to expand on, obviously to add an item here is relatively easy, but you can support backwards compatibility, and you can support a lot of other features with there's an ignore process, in that you can actually define out, I don't have an example of it, so I can get with you later, but there is a very well-defined process for versioning protofiles, and it is put in place by Google because they use the same concept of versioning, and the entire process is documented relatively well. And of course, I don't have an example of it, which is my fault there. Demo was getting pretty large at the time, so I kind of cut it short. All right, so another example of a problem that would lend itself well to gRPC is, say you had a shared legacy authorization or authentication process. You have it in some web forms app that was, 6 years ago, decided that we're going to put all of our security into some random database, and you want to share that. Now, you have a couple different options. Is you could obviously duplicate your authentication code. You can move everything to OAuth and just go full identity server or OpenID Connect, or you could, for example, take that auth code, move it into a gRPC service, and then your old systems can still call that as if it feels like a service implementation. So this is one of the things that are really nice about gRPC is when you use the client and call the service, it really feels and looks exactly like you're calling a service in an individual, or just like another service in the DLL or any namespace you're working with. So this is an example of me using that file service client, server client right here. I inject it using the built-in .NET dependency injection process, using that add gRPC client that I was talking about before, that manages all of the client connections, any sort of connection pooling, everything that you need. It's kind of managed through this HTTP client. Really nice little addition for anyone who plans to use it. And then when you actually use the method, it just looks like, right when I use it, because I'm not referencing the _1, it looks exactly like you are just calling another method from some service class that you injected. And that's it. You don't have to deal with, if there's an exception thrown on the other end of that gRPC service, it's going to propagate to your service. You don't have to handle a 500 error that's with special handling. You don't have to deal with any sort of custom authentication failures. There are ways of returning status codes from gRPC services. If you want to use it, there's a lot of benefit to it. But really, it kind of behaves exactly like you're calling a service in the solution. And this is a direct call to that. This is the NuGet package now.
Can you show that
Process.
code? So it returns a string from that call there.
This,
You're using that string to string the file.
yes, so in this situation, this download is calling the file server client. The file server, which is written in Node, is taking a stream from Mongo, piping it into the gRPC stream, and then I'm just reading this stream here and using it as if it were a regular C# stream. And so it's really kind of this seamless, and then that kind of gives you that ability to make a seamless stream throughout the whole process, which is how we do video streaming in this demo. In particular, so this is the implementation for Stream, and there is a backing database I can go into, as I showed you here. So in the video server has a backing SQL database. That backing SQL database has references to the video, to potentially videos that were uploaded in the file server, or in the case of, hey, we wanted to do webcam streaming, but we don't want to save the webcam file because, I don't know, that would be weird, but we didn't want to. So it's not like we're going to be writing a file over to Mongo. So now we have to have another backing store for our video server. So this is, again, going back to the distributed data concept, in that I have data going into this system that I need over here, and I have data coming into this system that I'm going to be reading from web, but these are all separate, and they come into, and we use it all in the web system. So one of the things I do is in the file server, when someone uploads a file, I emit an event. The event's picked up by the video server. The event has all of the video data. I project it into the SQL store. And now I have the external ID from the file server. It's all in my SQL store. I didn't really want to do a distributed transaction because it didn't really give me much benefit. So in this situation, my solution to this relatively simple problem was I'm not doing event sourcing because it was a pain in the ass, so I didn't want to do it. And so now I get all of the files that are uploaded to the file server. If they're videos, I store them in my database, and if I start a webcam, I store that entry in the database. Let's go back. So this is relatively easy in that someone requests a video, and let me just go ahead and start all this up since we are already over here. I'm going to start the file server, and yes, I could have used Docker Compose, but I did not. It would be relatively easy to set up, but I just have the services currently running under that is Spotify. That is not a gRPC service. All right, so let's start all of these ridiculous services and go to the actual demo. And what? So obviously we decided to make it somewhat like a very similar site that people might have seen called Twitch. But, and these are some videos I uploaded before. So another situation is, say some of our infrastructure team suddenly wants to migrate a bunch of videos over into this video service process. But there's no real active API, or there's no exposed external API for say if I had to upload video, but there is here. Either way, it's really easy to build tools to call into the gRPC service. So say you were building bulk upload tools. In particular, you were taking Excel files and bulk uploading it into some service, or if you were taking 100 terabyte video and you didn't want to download that through a WebSocket connection and you wanted to push it straight to the file server, you might build a small little CLI client from inside. And for instance, like this gRPC CLI client that we have. And this one's built in Node. It consumes, in this situation, it consumes the files proto, same files proto, but via NPM. And so we pull that in. We implement it as a client. You have this domain here is actually loading in the files proto. So it uses the proto loader, which is pretty much any tutorial on using gRPC for Node, you will find it. Load in the files proto, have the definitions, and so forth. And since I'm running out of time, I'm going to try and speed this up a little bit. So say I want to upload a video that I happen to have perfectly placed in an existing spot. And I like the Adventure Time Bacon Pancakes video, so I'm going to go ahead and upload that one. So we uploaded it. One of the people that kind of helped on some of this presentation, JP Dienst, who was going to talk but couldn't, decided that he wanted to spend a long time making a console-based loading bar, which is beautiful. It is definitely beautiful, but it may have taken longer to do the loading bar than actually upload the, than actually building the client. But it's cool. So now I just uploaded the file, the video server picked it up via the event, and you can see it. And now I go into here, and of course, hey, the audio is awesome. I'm going to pause that. So the video is streaming, as I said, from the file server into the video server, into the web server, and down to the browser over WebSockets. Now, how is it doing that? It's basically, the entire video is chunked. It's already transcoded. And if anyone wants to know about transcoding, I could talk to you later. Not important right now. You transcode the video and basically break it up into a bunch of really small chunks and then send it over the line one by one all the way up. So never at any point in time is the entire video in memory in any of these services, and it allows a streaming process all the way there. Now there would also be a process if you wanted to pause the video and stop the stream. You have two-way communication with gRPC now, right? So you can have the client then send the message all the way to the video server, say stop streaming, and then continue back when you want to start again. So that was a relatively quick demo of it working, and the last bit was, so now we want to conceptually scale this out. So each of these now gRPC services is an individual entity. So, and it's a relatively simple service and relatively easy to scale out. So you can just spin up 20 of him, connect to the same Mongo database, put a load balancer in front of it, and you have a distributed system. It's really no different from any normal API way of distributing or creating a distributed API. So gRPC is, we're very familiar with the majority of the ways to deal with scale in gRPC because they're very familiar to anyone who built a API at a scale. So, and last, obviously, we have comments, and we kind of just added this because it was fun, but the comment stream is the same way. So I can also build a client for, say, I built a small little chat client in .NET that can publish videos, comments. So I create a chat bot, and it does the same exact thing. You import the chat client. You can use this gRPC client to create it. All relatively simple. If you're curious about the specifics, obviously the GitHub is up, and I can talk to you afterwards, but we do not have as much time as I wanted for this presentation. All right, and so I just created a chatbot. And I can run 30 of him and he can do a lot, but I'm not gonna do that. And he was super simple to make, quick timer, sending messages. All right, last demo is, because of course we were doing a Twitch hybrid, we wanted to have live streaming. So as an example, let's go ahead and live stream the video and test this out. So I'm gonna go ahead and not get, I wish there was no, sure, there we go. I'm pretty sure the audio is running, but you just can't hear it. All right, so started a stream, see me over there, created an entry in the video server. However, this is not creating a file, so it didn't go all the way to the file server. But now you can start up that stream, and this is actually very similar to how you would build a real live stream, in that the so the entire process for this is every second I take a chunk of the video, encode it, which is relatively complicated in itself, push it up in a WebSocket, pushes it through gRPC, pushes it to Redis, which is then pub-subbed out to the other video servers, which then sends the package back to the web server and back down to the web client. Now, of course, that's way overcomplicated for a simple video app if you were doing it at a small scale. However, if you wanted to do this, and it's all delayed, so I'm going to go ahead and stop this. Very, very distracting. But it's just an example of how you can use this gRPC stream, how you can prevent basically memory constraints by using streaming and not have to deal with all the overhead of HTTP streaming, which anyone who has dealt with streaming large files and chunking things over HTTP probably have known that it's not the funnest thing in the world. But yeah, that's pretty much all I have.